The objective here is to describe what the Intel manual says about real number and non-number encodings. So as soon as I saw that non-number encodings, my mind immediately jumped to ASCII, but I don't think that's where they're going with this. They start by saying a variety of real numbers and special values can be encoded in the IEEE standard 754 floating point format. These numbers and values are generally divided into the following classes. So no, nothing about text or strings. Instead, it just says signed zeros, denormalized finite numbers, normalized finite numbers, signed infinities, nans, indefinite numbers. The term nan stands for not a number. Okay, we knew that. Figure 4-12 shows how the encodings for these numbers and non-numbers fit into the real number continuum. Every time I read that word, I think of Star Trek and the Q continuum. Well, they say that the encodings shown here are for the IEEE single precision floating point format. So remember, that's 32 bits. The term S indicates the sign bit, the E is for exponent, sig is for significant, and the exponent values are given in decimal. And then the integer bit is shown for the significance, even though the integer bit is implied in single precision floating point format. So they're just telling us they're about to show us the integer bit, even though it doesn't actually exist down at that low level. So maybe a good question for that first section, the introduction 4.8.3 section, a good question could be like, what are the classes, or what classes can these types of encodings be placed into? And so there's 6 of them right there. And here's that 4-12 chart for you to enjoy. An IA32 processor can operate on and or return any of these values, depending on the type of computation being performed. The following section describe these numbers and non-numbers classes. So first we have signed zeros. 0 can be represented as a positive 0 or a negative depending on the sign bit. Both encodings are equal in value, and the sign of a 0 result depends on the operation being performed and the rounding mode being used. Signed zeros have been provided to aid in implementing interval arithmetic, and the sign of a 0 may indicate the direction from which underflow occurred, or it may indicate the sign of an infinity that has been reciprocated. So I've never seen that term before. What is underflow? And then what does the manual mean when it says reciprocated? We've seen this word before. Well, maybe if we push on, we'll find some more understanding here. Non-zero finite numbers are divided into 2 classes. You got your normalized ones and denormalized. The normalized finite numbers comprise all the non-zero finite values that can be encoded in a normalized real number format between 0 and infinity. In the single precision floating point format shown in figure 4-12, this group of numbers includes all the numbers with biased exponents ranging from 1 to 254, and that's in base 10. In parentheses, they say unbiased. The exponent range is from negative 126 to positive 127. When floating point numbers become very close to 0, the normalized number format can no longer be used to represent the numbers. This is because the range of the exponent is not large enough to compensate for shifting the binary point to the right to eliminate leading zeros. Okay, so showing really small numbers seems to be problematic to Intel, or maybe to the IEEE 754 standard. So I'll simply ask what's wrong with numbers close to 0, and according to Intel, they're just saying that the smaller the number, the more to the right that mantissa, the binary decimal point there, the more to the right it is, and it runs out of room. And I just noticed that they're calling it binary point instead of decimal point, and I guess that makes sense. Well, when the biased exponent is 0, smaller numbers can only be represented by making the integer bit and perhaps the other leading bits of the significand 0. The numbers in this range are called denormalized numbers. And I guess that makes sense, going right back to the whole purpose behind a scientific notation. We're trying to save room on the paper, or in terms of memory, we're trying to save memory. Or if we're trying to represent a number very close to 0, we're going to have to lose some precision there and maybe knock off some of the significant numbers. So what I'm imagining they're saying here is, let's say we have this number right here, really close to 0, right? Well, just like before, we could go ahead and move that mantissa right there. But since we're running low on room, we can get rid of some of these least significant bits, or the smaller parts of the number, and kind of just treat those as zeros. Again, we're losing precision, but at least we're able to represent those. And just for fun, let's add a question here just to make sure you remember what single precision means. So how many bits are in a single precision floating point? And the answer is 32. Now, the use of leading zeros with denormalized numbers allows smaller numbers to be represented. However, this denormalization may cause a loss of precision. Oh, cool, I just said that. The number of significant bits is reduced by the leading zeros. Now, when performing normalized floating point computations in the IA32 processor, this processor normally operates on normalized numbers and produces normalized numbers as a result. Denormalized numbers represent an underflow condition. The exact conditions are specified in section 4.9, so we haven't gotten there yet. But moving on, it says a denormalized number is computed through a technique called gradual underflow. It's a good question, and at this moment, the only thing I know about gradual underflow is that it's a technique used where two numbers after being computed result in a denormalized number. Table 4-6 gives an example of gradual underflow in the denormalization process. Here the single precision format is being used, so the minimum exponent, that is unbiased, is negative 126. The true result in this example requires an exponent of a negative 129 in order to have a normalized number. Since negative 129 is beyond the allowable exponent range, the result is denormalized by inserting leading zeros until the minimum exponent of negative 126 is reached. Okay, so like it says before, you're just losing precision here, and I don't know why they felt like they needed to have this table show that. But I feel more comfortable with the concept of gradual underflow because they're just maybe showing us gradually, so bit by bit, they're going to keep knocking off numbers until we have this denormalized number that can represent what memory can hold. Well, they say in the extreme case, all the significant bits are shifted out to the right by leading zeros, creating a zero result, and the Intel 64 and IA32 architectures deal with denormal values in the following ways. It avoids creating denormals by normalizing numbers whenever possible. It provides the floating point underflow exception to permit programmers to detect cases when denormals are created. So that's nice, we'll know when we've lost this precision. And it provides the floating point denormal operand exception to permit procedures or programs to detect when denormals are being used as source operands for computations. And I think after covering, the normalized and denormalized, the concept of having signed zeros, and then, an introduction here on just real number and non-number encodings, this will be good for this video.